Welcome to a new section, Efficient Searching, Binary Search and Sorting. Searching is trying to locate a given value in a collection of values. In this section, you will learn about search algorithms, how to do efficient searching in a sorted list, and some sorting algorithms. Now we move on to the first video of this section that deals with search algorithms. In this video, we are going to take a look at linear search and binary search, and then compare the complexity of both. Suppose you are given an array of values, and you are required to check whether a particular value is in that array. What is the most natural way to find that element? Create a class with the name ArraySearcher. Now we will import util package. We will implement linear search. Well, it seems that the natural way is to go through each element one by one and check whether they match the given value. If any one does, we have found the element and we can return to the index. If not, we can return -1 at the end of processing all the elements to report that such an element could not be found. The function linear search takes an array of values and a value to search in it, and returns the index if the value is found. If not, it returns a special value, -1. The program simply goes through each element and checks whether the current element matches the value to look up. If it does, then it just returns the current index. Otherwise, it keeps looking. At the end of the array, it returns the special value, -1. Now we will check the linear search function by calling it from the main method. Implement the main method. In the main method, we have created an array. Then we searched for two elements, 5 and 23. This should give -1 for the first case and 5 for the second. Let's run it. So here it returns -1 because 5 is not present in our array. Then it has returned 5 because 23 is present at index 5. Now, if we have a list of student names and their corresponding marks, and we would like to search a student name and the marks would appear, we could use linear search. We just need to have the marks of the student stored in a different array in the same order as that of the student. Here there are two arrays with the name of students and their marks. Now we can write a function to search for a name. This is the function marks for name. First, we look for the name of the students in the list of students. If the name is found, the corresponding index would be assigned to the variable index, and the value would be greater than or equal to 0. In such a case, we return the marks stored in the same index as of the marks array. If it is not found, we return null. Now go to the main method. We will look for the marks of Mary. Remove the previous search. When we run the program, we get the marks 65. You can see that Mary is stored at index 2, and the marks stored at index 2 are 65. So, this worked. What is the complexity of linear search? We have a for loop that moves through each element of an array of length n. In the worst case, we would go through all the elements, so the worst case complexity is theta of n. Even on an average, we would be visiting half the elements before we hit the correct element. So, the average case complexity is theta of n by 2 equals theta of n. Now let's move on to binary search. Is a linear search the best we can do? Well, it turns out that if we are looking at an arbitrary array, this is what we have to do. After all, in an arbitrary array, there is no way to know whether an element is there without potentially looking at all of them. More specifically, we cannot say for sure that some element does not exist without verifying all the elements. The reason is that the value of one element does not say anything about the values of the other elements. But what information can one element have about another element in an array? One way to make elements have information about the other elements is to have a sorted array instead of just an arbitrary array. What is a sorted array? A sorted array is an array that has all the elements arranged in order of their values. When an array is sorted, Every element contains the information that everything on the left is smaller than that particular element, and everything on the right is bigger, or the other way around if the order of the elements is opposite. But we will consider the arrays that are sorted in an increasing order from left to right. This information can amazingly make this search a lot faster. Here is what we do. Check the middle element of the array. If it matches the element we are searching for, we are done. If the middle element is smaller than the value we are searching for, search on the subarray on the right of the current array. This is because everything on the left is even smaller. If the middle element is bigger than the value we are searching for, search only on the left subarray. To avoid creating copies of the array while creating a subarray, we just pass on the whole array, but we remember the start and end positions we are looking at. The start is included in the range and end is excluded, so only elements on the right of the start position and the left of the end position are included in the subarray being searched. But before implementing this algorithm, we need to understand the concept of comparable. Comparable is an interface in the Java standard library that looks like this. Any class implementing this interface has to compare a different object with itself. It is required that the type parameter, t, must be instantiated with the same class that implements it, like this. The compareTo method intends to compare an object of the same type. If the current object, the one that this reference refers to, is smaller than the object passed, compareTo must return a negative value. If the object passed is smaller, the method must return a positive value. Otherwise, if they are equal, it must return 0. Now we write the search function to do the search. The first if condition checks whether the array passed is empty. If so, obviously the element to be searched is not found, and we return -1 to represent this. Then we find the mid-index, and if it matches, we return the mid-index. Then we recursively search for the element in either the left or the right subarray. Once we have this function, we create another wrapper function to run the search without having to mention the start and the end positions. This is the wrapper method binary search. This calls the binary search method, which takes the sorted values, value to search, start and end indexes as parameters. Note that in this case, we have mandated that the objects in the array must be comparable so that we can know if an object is greater than or less than another object. It does not matter exactly how this relationship is determined, the array must be sorted using the same comparison. That the comparison between two consecutive elements will make sure that the element on the left is smaller than the one on the right, as provided by comparable. Let's look at the complexity of the binary search algorithm. In every step, we are partitioning the total array into two parts, barring the one element that we are comparing. In the worst case, that is, the case where the element search is not present in the array, we will have to get down all the way to the point where we are dealing with an empty array, in which case we return -1 and stop recursing. We must have had an array of only one element in the previous step. For our analysis, we will consider this step as the last step. So, let's have a sorted array of n elements, and t of n is the time required for searching in the array. In general, the two search branches of every step would be of different sizes, one potentially being of size 1 less than that of the other part. But we will ignore these small differences, which hardly matter for a large n. Hence, we will work with the equation shown here. Now let's assume that n is an integral power of 2, so that n is equal to 2m for some integer m. So we have this. Now we take another function, s, such that s of m is equal to t of 2m for all m. Then we have this. This is the formula for an arithmetic progression, and hence we have this result. So we have the asymptotic complexity of t of n. The function t of n grows only as fast as the algorithm of the size of the array passed, which is really slow. This makes binary search an extremely efficient algorithm. Now go back to the main method. Remove the previous methods that were entered. To sort of field test the algorithms, we run both linear and binary search algorithms on an array of 1,000,000 elements. This is the resulting code. We have tracked the time taken by both the algorithms. On my computer, the linear search took 48 milliseconds and binary search took 0 milliseconds. Also note that the value we are looking for is expected to be quite near the beginning of the array. In case of values near the middle, a binary search would have an even higher advantage. So we looked at two search algorithms, linear and binary.